Yeah. What's today? 7? Yeah. Oh. I have signed my life away. Go
Yeah,
ahead.
great. So our first speaker this up. So our first speaker of the afternoon is going to be Carey King from Austin University in Texas, and he's going to talk about the title of his talk.
I'm going to talk about the title of this talk. So, yes. Okay, thank you. So it's a pleasure to be here. I was lucky enough to be here last one of these conferences, and I thought it was so great that I would come back. So thank you very much for inviting me back, because I enjoy the conversation so much. So this talk is about my wanting basically to teach myself macroeconomic modeling to answer, or at least try to address, a lot of questions that people have had about how the structure of society relates to things going in the economy, or how energy flows and resource flows affect the structure of society, or if you can even tell the difference, how would you even think about it? So this is my attempt to do that at a very high level. So what I'm going to show you is a model that has no relation to anything in the real world, but it's the structure that is important. But before we start there, I'm from America, so I have 2 words for you: Trump socks, okay? I have socks, and I brought my comb to keep him nicely prepared. So I have help from the university for this. So there you go. So that's my Christmas gift. My first time wearing them. I haven't worn them yet, so I have my Trump socks to keep me warm. This is not what my talk is, but some people have asked questions that I think this paper relates to. I will post, this will be stated on my last slide, so you can write down the title of the paper. But this is really the talk from yesterday about Joseph Tainter and understanding energy complexity. That was the motivation for this paper, and I tried to quantify how the United States economy has changed as it relates to energy, and I think it has interesting findings that roughly support the idea. Okay, so my goals for wanting to understand macroeconomic modeling, to understand if and how the finite Earth is having some effect on data that we can find out there. Data that's economic data, how much people are getting paid in wages. Is debt accumulation something related to resource constraints? How would we know? How would we prove that? Can you prove that? And then, of course, data tracking energy uses and flowing. Broadly speaking, but my model is trying to understand, or at least the motivation is to try to understand the transition from, say, agrarian to industrial economy. And if we can understand that, or feel like we have some understanding of that, then I might be able to say something about going to a low carbon future from roughly today. So people have asked questions about calibrating models and how would you know it's true. My model is not going to convince you that anything it is true. It's more important this is the first time I presented results, so it's not a published paper. But I'm thinking in a very broad context, I want to represent some basic trends from the agrarian to fossil transition. And I haven't yet met Oster if she's in here, but her work is certainly related to this, looking at historical data. So what do I mean by tracking a very broad trend? These are data by Roger Fouquet at London School of Economics, but I've plotted in this nice colorful graph. And I'm using the sustainable pointer. How much money is spent on fuels that are related to certain energy services. So the service of power in agrarian society is mostly provided by biomass being fed to animals, and they are doing the work on the farm. So that's about 20 or 30% spending relative to GDP of pre-industrial England. If you add on the food related to the costs related to the people that are also working on the farm using their muscles, it's another 30%. So 50 to 60% of England pre-industrial, the cost of energy to operate an agrarian society was equivalent to 50 or 60% of GDP, and then it declines once you get full kick-in of the steam engine, and use of coal declines to less than 10% by the time you get to the World Wars era. So this is the broad trend that you would need to replicate, something where you have a relatively high percentage of GDP spent on energy to something that declines quite drastically over the span of 100 years or something like that. So there are biophysical models, what we call biophysical models, things just tracking people and resources, capital sometimes, but avoiding the concept of money. Then there are economic models that talk about moving money around. They might talk about population, capital in one form or another, but they certainly focus on tracking money, and they may or may not track physical things. So the idea is, well, can I find a simple model of a biophysical economy and a quote-unquote simple economic model? Turns out it's not so simple, maybe, and then combine them together. So that was my motivation. What can I find the simplest models in each domain and put them together from the beginning? So to do this, the biophysical model I use is this handy human and nature dynamics model. If anyone's read this paper or familiar with it, essentially has 4 equations. So it seemed to be one of the simpler models I could think of that had the capability of preventing infinite growth. So this model basically says you can't grow forever because of its basic structure. It's a sort of predator-prey type framework where humans are the predators preying on nature and extracting resources from nature. So it is the way it's configured and the way I still use it and what I'll show you is as it's like a regenerative stock nature, so it's essentially like a forest. So nature and what I'm presenting you is like a forest. It's not fossil minerals, it's not solar, it's just like a forest. So I simplify into 3 equations. So I have births and deaths of the population, nature, extraction. I'll go over these parameters a little bit, minus the consumption of nature. What they call wealth is essentially what you extract from nature, but you have not yet consumed. So in their model, wealth can accumulate. So what are the finite world pieces of their model? So they have this lambda parameter. That's defined as the maximum resource size. So this is basically the one factor that says this is how big the Earth is, or the world is. It's some maximum size of the forest, if you will. The death rates are a function of wealth. I make them a function of the extraction rate. So essentially, death rates, if there's enough nature being extracted for people to consume, means they're relatively healthy. And the death rates are low. If there's not enough nature per person or extraction per person, then the death rates can be higher and population can go down. So this is the feedback that prevents population from going up indefinitely. There's the regeneration rate, this gamma. This is basically the rate at which the forest replenishes itself. And they have the extraction term. So they have a delta here is a parameter for the tuning parameter to play with to say, how fast do you extract per person in their case, and it's multiplied times the quantity of nature, y. So if nature goes to 0, like you've depleted everything, well, you can't extract what's not there. So this is the feedback to prevent you from extracting everything. They have it as a function of people because they're modeling an agrarian society. I change it to a function of capital because I want to understand something about investment and money flows in the economy. So these are sort of the main factors to understand from this model. What do you get from this model? Here's an example result from their paper. If you have what I'll just call a moderate extraction parameter, delta, means you're not extracting things too slow so that people die because there's not enough wealth being extracted, or nature, and it's not so fast that you deplete everything, you can end up at a steady state and everything seems hunky-dory, everything seems okay. So this is a typical kind of result. If you change the extraction parameter to something too high, then you can extract all of nature and take it down to 0, and once you do that, eventually everyone will die because you've extracted everything and you've depleted the natural resource stock. So you can get this effect even from a forest, say, concept, which is what's embedded in this model. So that's the summary of the handy model, at least the simple concepts that I'm using from it. The economic growth model is very similar to what Sandra presented 2 days ago, I think. It's got some kind of quote-unquote standard kind of stuff in there. There's capital accumulation. I have 2 sectors in the model. So there's the sector that extracts resources, and there's the sector that magically does everything else in the economy. I just call it the goods sector. So there's 2 sectors, the extraction and the goods sector. So capital is accumulated in both sectors. Capital that extracts resources, there's capital that does other things in the economy, including produce more capital. And each one can have debt accumulation potentially. The debt is investment minus profits. So however much money you invest, if it's bigger than your profits, the assumption is you've taken a loan out from the bank and you're paying interest on that. Or you're taking a loan out effectively from households that are putting money deposited in a bank and giving it to you as a company. The investment function is something I just take from the work of Steve Keen and what Gaël Giroud and Sandra and that team is working on, which is one way to do this. It's essentially that investment is a function of your profits, or your profit share in this case. So this has the capability of simulating something like a financial crisis, or if people are familiar, the sort of Minsky instability hypothesis idea. So you can accumulate debt, which means you're accumulating interest payments, which means you could potentially pay so much for interest that you collapse the economy because you can't pay for other things like wages or other necessary parameters, or have profits. The wages are dictated by a Phillips curve, so this is also something, I guess, fairly standard in at least unorthodox economics. What a basic idea is, if employment is above a certain set employment rate, wages increase. If employment is below that certain set point, wages will decrease. The idea is that if I have high employment, people have more bargaining power to ask for higher wages. If you have low employment, they don't have as much bargaining power to ask for higher wages. So this is the dynamic that gives a feedback to increase wages, therefore decrease profits, decrease investments, and then it gives an incentive of firms to fire people and cause employment to happen, or unemployment. All right, so now I'm going to go through a set of flows to show you what I'm modeling inherently, and then I'll show you the economic framework and some example results. So there is nature out there. It's like a forest. The nature is used to do four things when we extract nature. So this is a stock of nature. This is now a flow of nature that we've extracted. Some of the nature goes to extract, or goes to operate extraction capital. So it's like I need fuel to operate the machine, the oil rig, or I need fuel to operate the machine that tears down forests, right? It needs forests, so this capital is needed itself to extract nature. There is also nature input required to operate goods capital. So there's two kinds of capital in my model, that extracts and that produces goods. Both of them need fuel or nature input. A third thing that happens is humans consume nature relatively directly. Either you can imagine it consuming it in your household as electricity or as food. Nature here is so generic, it's just resources extracted from the environment. So some of it goes to food. So the green here is kind of units of nature. You go through the price and you can end up with money. So the yellow here is in units of money. There is also, the fourth thing is that there is nature embodied in capital. If I want to make capital or physical structures, it's made of resources, it's made of natural resources, so we calculate how much nature is involved in investment. So the embodied nature in investment, and then we can calculate that as money as well. So this investment goes to two things. Again, some of the investment goes to make more capital goods, some of it goes to make more goods for extraction. We go through the price of what goods are, and we end up with units of goods. So this has a mixture of units of nature, goods, and then converts both to money through prices. The goods capital produces goods. Goods output, these goods are either directly consumed by people, households, or, as I've already stated, they go into basically become investment by multiplying times the price of goods. So this is essentially the flow or the concept that I was wanting to put into an economic framework. And the economic framework is often represented by an input-output table kind of framework. So for those not familiar, so the columns are these two. The goods column, for example, these two terms are the purchases of the goods sector. These two terms are the purchases of the extraction sector. The rows represent the sales of the sectors. So the top row represents the sales of the goods sector, and the second row represents the sales of the extraction sector. There's consumption of both sectors, and then the investment. Since the goods sector produces investment as its output, both of the investment parameters quantities show up in the goods sector. So I'll go into how you put the diagram I showed on the previous slide into the parts of this input-output matrix. So this A sub EE term is basically the nature requirements for the extraction sector itself. So it requires some nature input to operate its capital, and then this term is phrased as the fraction of total extraction output that is required to operate the nature capital. So in this case, I have some efficiency parameter that says how much nature is required to operate a unit of capital. The CU is capacity utilization, so you have the potential to have a quantity of capital that doesn't operate at its full capacity. And then the bottom term here is the same as the handy model, but I've replaced humans extracting nature with capital, so it's a delta extraction parameter that you can play with. Y, the quantity of nature, capital, times its capacity utilization, so you end up with a term like this, in which Y is a state, the quantity of nature, affects how much energy or how much nature you need to extract or to operate capital is affected by how much nature is actually still present in the environment. So this is a feedback for that. This term, this AEG term, this is how much nature it costs, how much nature input is required by the goods sector. And there's two terms here. There's an operating term and an investment term. The operating term is similar to the operating term that we just discussed for the extraction sector. So this is essentially how much nature do you need to operate the goods capital divided by the total output of the goods sector. So this has the same framework, some efficiency parameter times the capital and its capacity utilization. This is a generic Leontief goods output. I just have a fixed capital output ratio, which is the V, and then the quantity of capital also dictates its output. So you end up with a, for my purposes, a constant parameter for the quantity of nature required to operate a unit of goods capital, or a unit of goods output. And then there's the investment term. So because investment requires goods, or investment requires nature, because capital is made out of resources, this is investment in units of money divided by the price of the extraction sector, so that converts it to units of nature, and divided by, again, the gross output of goods. So this is kind of the key linkage to internally calculate embodied energy in investment. So you can calculate things like net energy ratios or stuff like that. So the purpose here is to try to have a model that can present all kinds of metrics in units of money and units of resource flows. So I'll show you some example simulation results. Here's my caution. Nothing is calibrated to the real world. I've kind of just figured this out. So the important thing is just to look at the trends and how they change with a kind of sensitivity analysis. Right, 5 minutes. All right, so here's some example results. I'll go over some of these. So I'm changing the efficiency of operating the capital. If I change this is a low efficiency for the blue, a little bit higher efficiency for the green, a little bit higher for the orange, and higher for the red. So in this particular case, just notice that the red is higher than the blue. If I'm more efficient at operating capital, there's more nature available to make more capital. So I accumulate more capital. This graph is the total amount of capital accumulated. If I'm more efficient at operating, I have extra resources to make more stuff. Here is the population. Similarly, if I'm more efficient at operating my economy from a nature standpoint, I have more nature left over for people. People require nature, a certain quantity to survive. I'm able to have a higher population. Here is the fraction of capital that is for in the goods sector. Of course, 1 minus this is the fraction of capital that's in the extraction sector. If I'm more efficient at operating my capital, I'm able to have more of the capital be in the goods sector versus the extraction sector. Here is the nature extraction rate. If I'm more efficient, again, I'm able to have a lower end extraction rate. The rate at which I'm pulling it out of nature can be lower for the same, for the equivalent other states of the economy that have been in the other slides. Because I have all these separate pieces, I can calculate what people are calling the EROI, but in this case I call it a net external power ratio because it's unit of flows of nature divided by a unit of flows of nature, so that's more like power over power. So this is the net output, the net extraction output divided by the extraction inputs required to operate extraction capital and make new extraction capital. So this is the EROI, if you will. If I'm more efficient in operating my capital, I end up having a back calculated metric here higher than if I were not very efficient at operating my capital, right? So you can kind of see how this parameter would change. All right, so what if you have so those examples had no debt accumulation. So what if you have debt accumulation? So the red is similar to an answer I showed you already. And if you have debt accumulation, which essentially means I've changed one of these investment parameters that tells me to invest more than my profits. This is the wage share. The wage share can decline. So depending on what parameter you choose, the wage share declines further. Now, why is that? It's basically because you are accumulating debt now I have a constant interest rate. If I accumulate debt, I have to make interest payments, and these interest payments are taking up my ability to continue to pay the same wages to the workers. So the trade-off, I make interest payments, don't pay workers. Keep the same level of profits. Some of these other metrics don't change a lot. The total amount of capital hasn't changed much due to debt accumulation, and this net external power ratio, or EROI, also metric, has not changed much due to debt accumulation. So, all right, so now I'm going to say, what if you found more resources? I'm just going to kind of go through a hypothetical here because I'm wondering what this model can do and it can't do. So what if I found more resources? I said I wanted to calibrate something where I just find, the Industrial Revolution happens, I decline the quantity, the spending on energy divided by GDP. So that's represented here. I go, all of a sudden, I find more resources. This is the percentage spending, energy spending divided by GDP, and it declines to some degree. So this is not change in technology. This is if I just found another forest of the equal size and like, oh, there it is. Same technology, spending on energy goes down in a similar manner as that, even though the Industrial Revolution is not that simple. So the same hypothesis, what if I found more resources? So that's what's represented here. This is the quantity of nature that's out there. All of a sudden I find 100 units more, so it goes up by roughly 100 units. Then I extract some more. If I have no debt, the red line, again. If I have debt, then I have the orange line. So strangely, nature can continue to increase, reforestation, if you will. If I have debt accumulation, I've taken wages from people, implying population's going down, and so there's less consumption by people. The nature extraction rate goes up about fourfold in this case, if I double the resource size. Here's the net external power ratio, or the EROI, if you will. If I find more resources, of course it goes up. I've got more resources, and again, the net external power ratio goes up as I accumulate debt. That's something interesting to think about, whether that seems to be a real effect or not, but a linkage between debt and the appearance of resource quality. Total net output, so this is GDP. If I find more resources, GDP goes up. Again, it increases continually if I have debt accumulation. So here's another check with the economy, last couple slides. So I'm interested in the wage share. So the wage share, if I have debt, is this orange line. If I find more resources, the amount I can pay to wages goes up, and then eventually follows the similar trajectory, declining as it did in the past. So speed up. All right, so might this follow something in the real world? So this is data from the United States on employee compensation. It's not exactly wage share. This is wages plus insurance benefits and plus pension benefits, so total compensation. So as a share of GDP, it goes up and then stabilizes in the 70s and kind of goes down. All right, so what about that? What if starting in the 1920s, we could say something like the oil age really kicked in and we started consuming a lot of oil, wages went up. Our wages as a share of GDP went up, just like this, my simple little model says. Then they kind of peaked out, and then they started continuing down when we had the era of debt, basically. The era of debt accumulation starts in the 1980s. Interestingly, this white line is the energy consumption per person in the United States, or total primary energy consumption per person. Also kind of follows this trend of compensation, so we can really start to ask if compensation is related to resource extraction. So that's the end of my presentation. Thank you.
So thank you. We have time for a few questions. Oh, okay, let's start from above.
Hello, and thank you for the talk. I'm wondering, when you talk about interest payments, I didn't see any bank in your sectors, so there were just the goods sector and the capital sector. So do they leak somewhere, or do they come back to the sum?
A bank is, in my model, a bank is magically just there to take the savings of consumers and give it to firms. Or I guess the other way around, the firms invest, and by definition, that becomes the savings of the consumers. But the bank doesn't make profits in my model.
So if the bank doesn't make profit, then all the interest payments go back to the purchasing power of people.
Yes.
So it shouldn't.
Yes.
I mean, it's another way of paying wages somehow. So it shouldn't have a net effect.
So I didn't show interest payments plus wages that are going to households. I didn't show that graph, so I'm agreeing with you. Yeah, the interest payments are in the model still going back to households as compensation. I have to be more specific on the economic activity with the negative effect. So I just plotted wage share, but if I'd plotted interest payments plus wage share, I guess it would have still been flat. It would have looked like nothing was wrong. Right. So if we get a more complicated model that says only some portion of the population gets interest payments and another population gets wages, then you can start to talk about inequality, but this doesn't have two kinds of populations. So I can't address that question yet.
Very interesting talk.
You're right.
Did you try to link the interest rates with the efficiency of your extraction? When you have a high extraction, you have high interest rates, and when it gets lower, you have reduced interest rates, which seems to be what's happening right now.
I would like to do that. I've in previous models that I didn't believe were working in a manner that was reasonable. I was playing around with that, but that's what I want to do that. I don't have a result for that. So yeah, link interest rates to debt, GDP, or rate of extraction, some feedback to dictate what interest rates, how they would adjust. So yes, I would like to play with that. That is a goal of the model, yeah. A goal of the work, yeah.
Thanks for the presentation. A short technical question. The time scale you have, it is running in hundreds of years.
Compared to see the slide, the results don't mean anything in the real world. Yeah.
What is behind it? How do you get the time scale? What is this autocatalytic? I think you must have in the equation somewhere autocatalytic power multiplicative term, and this coefficient in front is 1 over time. So it is in your equation. It must be somewhere.
What are the things that are, I guess,
if you have x point equals alpha times
what's
x,
dictating the
alpha is 1 over
oscillation time period? I guess is that your question? What's dictating the oscillation time period? Right. The rate of the population growth assumptions, birth rates, the death rate, the wage. One of the most important ones is the shape of this wage function. So it dictates how fast wages change as employment. And so if you have a very steep wage function, then you can get very tight oscillations. If you have a very slowly sloping wage function, then you can get longer oscillation. That's one of the more important parts. So if you calibrate this to the real world, that's one of the more important things to do.
Sorry, we have to move on because we have many speakers and we have to keep time track. But you know where to find him anyway to continue.
Thank you.